What do you mean by monotonic sequences? Suppose, okay, please, all of you, mute your microphone. Please mute your microphone. So suppose xn is a sequence. Xn is a sequence. Okay. When I say this sequence is monotonic sequence. When I say this will be a monotonic sequence, either if it is monotonic increasing sequence or if it is monotonic decreasing sequence, then that sequence is called monotonic sequence. Now, what is monotonic increasing? If the terms are increasing as n increases, like I can say that xn always less than equal to xn plus for all n. If this thing happen, then we say it will be a monotonically increasing sequence. If the equality sign is not there, then we say it is strictly monotonic increasing. Okay. If simply we have xn less than xn plus 1, then that is called strictly monotonic increasing. And for monotonic decreasing sequence, xn will be greater equal to xn plus 1. And this is for also this is for all n. Then we say this will be a monotonic decreasing sequences, and if equality sign is not there, then it is strictly monotonic decreasing sequence. And the constant sequence is also is a monotonic sequence because equality for this equality sign, that could be falls under increasing or decreasing both. Okay, so we can say it is a monotonic sequence. So some if we take some example, like suppose xn is equal to whatever we have done in last class, that is 1 1 by 2, 1 by 3, 1 by 4, 1 by 5. You see, it is monotonic decreasing sequence. The monotonic sequence, this one. Again, if I take 1, 2 square, 3 square, 4 square, 5 square, like this, it will be monotonic increasing sequence. But if I consider the sequence like 1 minus 1, 1 minus 1, 1 minus 1, like this sequence is not neither monotonically increasing nor monotonically decreasing. So this sequence is not a monotonic sequence. But the constant sequence, if I take like 2 2 2 2 like this sequence is also a monotonic sequence. Okay, so like this we can define the monotonic sequences. Now there are some facts, like we study some facts. First of all, we have studied that sequence may be convergent, may not convergent. So that depends upon the limit. For I am talking about only the real sequences. So if limit n tends to infinity xn. Okay, please, someone is shouting. Mute your microphone, please. Hello. Please, all of you, mute your microphone.
Navin's mic is on.
Praveen, turn off your mic.
Okay. Limit n tends to infinity xn is equal to, if some finite value, this some finite value, then we say this limit this sequence xn is convergent, otherwise not convergent. Okay, uh, finite and unique, I can say finite and unique, then only it is convergent. Like if it is convergent, it converges to unique limit. If it is convergent, it convergent to unique limit. Next is third one is very important, that every convergent sequence is bounded but not conversely. So every convergent sequence is bounded. So if I consider, like suppose xn is equal to 1 by n square, a sequence, if I consider xn is equal to 1 by n square, you see the limit is what? N tends to infinity, xn will be equal to 0. So again you see the sequence is 1 1 by 2 squared, 1 by 3 square, like this it will go. You can see, you can check that this sequence is a bounded sequence. Why it is bounded? Actually, if you go back to the definition of convergent of sequence, there you can see that we always have some epsilon greater than 0 when, and there exists some epsilon greater such that xn minus L is the L is the limit is always less than epsilon. That is what? That L minus epsilon less than xn less than L plus epsilon for all n greater or equal to some fixed value of n. Okay, that means what? This xn is always bounded by two numbers. So that's why every convergent sequence will be bounded sequence, but not the converse. So to show that the converse does not exist always, you have to give some counter example. So what will be the counter example? If suppose if I consider a sequence 1 minus 1 1 minus 1, you see this sequence is bounded sequence, yes or no? 1 minus 1 1 minus 1 it is go. So you see all the values lies in between 1 minus 1 and 1, so I can say this is a bounded sequence. But you see this sequence is not convergent sequence because it is converging to two limits. The limits are 2 1 and minus 1. So as x tends to infinity, either it will be 1 or it will be minus 1. That means it is oscillates between two finite values. So it is an oscillatory sequence. It is not a convergent sequence. Every convergent sequence is bounded, but the converse is not true in general. Okay. Okay. Now go to the next slide. Again, some few properties that addition property, multiplication property, all holds here. Uh, you see, limit n tends to infinity, xn plus minus yn. This will be summation of two limits of the sequences. If xn and yn are two sequence where xn converges to, suppose xn converges to L and yn converges to M. If this happen, then xn plus yn, the summation some sequence will converge to L plus minus M. Similarly, for the product and division also hold. But in the division case, we must have this limit not equal to 0. Okay, there are some this type of properties we have. These are all we have done in last class, but for the technical class purpose,
Can
we
you
are
please
not
explain this
getting.
again? Sir, can you please
Which one?
explain this again? Sir, this
Which one?
sir, this one. This one.
Okay. Suppose we have two sequences. Xn is equal to, suppose, okay, let me explain. Xn is equal to 1, 1 by 2, 1 by 3, like this it is going. Okay. And another sequence yn is equal to, we have suppose 1 1 by 2 square, 1 by 3 square, like this it is going. Two sequences. This sequence tends to 0. Okay, both are tending to 0 actually. This sequence also tends to 0. So the sum sequence, that means xn plus yn, what will be your xn plus yn? This will be 2, then 1 by 2 plus 1 by 2 square, 1 by 3 plus 1 by 3 square, like this. This is another new sequence. If you know that this sequence tends to 0, this sequence tends to 0, we don't have to find any other limit. You can immediately say this sequence also tends to 0 plus 0, that is equal to 0. That is my point. This type of things also holds in the multiplication case and division case. But for the division case, you cannot take this example because as limit y tends to yn tending to 0, in that case it does not hold. Okay, in that case it will be 0 by 0, which is undefined, so it does not hold like
I have
this.
one doubt.
Okay.
Sir, you showed one
Okay.
sequence there that 2, 2, 2. I mean, it's a constant sequence. So
Yes,
it should be it's a monotonic sequence. But sir,
it is a motoring sequence.
then sir, we cannot classify it as increasing or decreasing because each term is equal.
Yes, yes, you can classify as increasing or decreasing. Not strictly increasing. You cannot say that strictly increasing sequence. You cannot say that strictly motor, strictly decreasing sequence. But you can say increasing sequence or decreasing sequence. That's why I'm used the term that strictly. Strictly means it is increasing strictly or decreasing strictly.
Sir, what is the meaning of
Okay.
x
Thing
and
is that
by yn?
hmm,
There,
So
how to write xn by yn actually?
this xn by y 1 by 1, 1 by 2 by 1 by 2 square,
Means
1 by 3
term-wise
by 1 by
division.
3 square, term algebra.
And same is true for multiplication also.
Same is true for
Okay, sir. Thank you.
Sir, is this only applicable
yes.
for infinite series, these three properties?
Yes, I'm not going to see series now. This is all about the sequences.
Only when limit n tends to infinity or limit n tends to some finite number.
No, limit n tends to infinity always. Because
Okay,
sequence
sir.
is the okay. Now come down to the series. Actually, we have the in our syllabus the series, infinite series, basic idea we need. That's why we are talking about. Now consider uh, un is a sequence of number. Un is a sequence of number as u1, u2, u3, u4, u5 up to n, up to infinity. A sequence of number. Then if we write the sum u1 plus u2 plus u3 plus up to infinity, then this is called an infinite series. If the if you write up to some finite value u1 plus u2 plus up to un, suppose, so in that case that is called a finite series. But if I use up to infinity, then it is a infinite series. Our aim is to check, you see, now as infinite terms are there, you cannot say you will have a finite sum for this or infinite sum, that you cannot say. So that's why we need to check whether it is will it have a finite value or infinite value. That is our motto in this area. So we define this as n is equal to 1 to infinity un, or sometimes we simply, if we write summation un, you have to understand that this is actually n is equal to 1 to infinity. We are talking about only infinite series. Okay, so now if it is an infinite series un, summation u1 plus u2 plus u3 up to infinity. Now we are considering another sequence. We construct another sequence, that is Sn. What is Sn? Sn is equal to u1 plus u2 plus un. This is called nth partial sum. Nth partial sum of the series. So nth partial sum. So Sn is equal to u1 plus u2 plus up to un. So similarly, S1 is equal to u1, s2 is equal to u1 plus u2, s3 is equal to like this. So we are constructing another sequence. So this is a series which coming from one sequence, and now I am constructing another sequence. This is called the nth partial sum sequence of this series that we are considering. Now if this sequence Sn tends to S as n tends to infinity, this sequence of nth partial sum, if this sequence converges to some finite value s, then we say this series is convergent and the sum will be s. So this is the definition of convergency of the series, that if the nth partial sum Sn, n tends to infinity, this converges to some finite value s, then we say this will be this series will be a convergent series and converging to the finite value s. Okay, so consider summation un. Summation un is equal to 1 plus 1 by 2 plus 1 by 3 plus 1 by 4, like this infinity. So it is coming from the sequence 1 by n. This is coming from the sequence 1 by n. Now here Sn is equal to what? Nth partial sum, that is equal to 1 plus 1 by 2 plus up to 1 by n. Okay. Now if this Sn tends to some finite value, then only say this series will be a convergent series. So now we have to check whether this sequence Sn, S1 is equal to 1, S2 is equal to 1 plus 1 by 2, S3 is equal to 1 plus 1 by 2 plus 1 by 3, like this. If this sequence convert, then we say there is a converging this series is convergent. Okay, we'll when we study P series something, there we will study that this particular series is not a convergent series. That we will study later. Okay, so for the time being, you just try to understand what I'm saying about the infinite series. Okay, now Next we go to the convergency of the series. So in this chapter, actually in infinite series, our aim will be always to test a series will be given to you, a series, whatever a series will be given to you, infinite series must be, will be given to you. You will be asked to verify whether this series is a convergent series or not. So you will be given a series, you will be having one series in your hand, and you have to check whether this series is convergent or not. You see, if we able to judge a series is convergent, infinite series is convergent, if it is able to judge that it is guaranteed that it is convergent, then by using some computer or etc. or sometimes in some mathematical way, we can get the value. But if it is not convergent, if you find that not convergent, so you cannot get any value by using some other. Okay, so always first you need to test whether this series is convergent or not. So in your syllabus you will have only to test the convergency, not to find the value. Okay, so for this we will first study the necessary condition for convergency of a series. So suppose we have a series summation un, n is equal to 1 to infinity. Okay, so un is the nth term. That means this is u1 plus u2, like this it will go. So what is the necessary condition? Necessary condition means if it is a convergent series, that if you know that this is a convergent series, then we must have the nth term, limit n tends to infinity, un must be equal to 0. This is the necessary condition, not sufficient. That means if somewhere if you get that un tends to 0 as n tends to infinity, then you can immediately say that this series may be convergent series, not guaranteed that this will be convergent. But if you somewhere find that limit n tends to infinity un is not equal to 0, then you can immediately say this series is not convergent. Understand? So if this is the thing of necessary condition, that if it is convergent series, then this thing must hold. That means if it is not hold, that means it is not convergent. So you can say that if it is not, so first thing you need to check for a series to test the convergency. First you need to check that whether limit n tends to infinity even this. So if I give one like this, summation n by n plus 1, summation n by n plus 1 is one series, n is equal to 1 to infinity. You see, un is equal to what? N by n plus 1, and which is tending to 1 as n tends to infinity, yes or no? Okay, so this tends to 1 as n tends to infinity, so immediately you can say this series will not be a convergent series. But suppose if you have n is equal to 1 to infinity 1 by n, here you see 1 by n tends to 0, but you cannot conclude 1 by n tends to 0, but you cannot conclude that this series will be convergent. You can say it may be convergent, there is a chance that it will be convergent. So this is the thing of necessary condition. So now we will study two particular type of series, and with the help of that series, for any arbitrary series we can test the
Sir,
convergence.
one please repeat it.
So
I can't understand that point.
which one?
So at this point, sir, the n plus one un is equal to n by n plus 1, and that the next necessary step, sir.
Okay, actually you see this is a necessary condition. I am saying limit n tends to infinity even is equal to 0. That means this is a necessary condition, means if you know that this is a convergent series, then you can say this thing. But if this thing occurs somewhere, you cannot immediately say that this series will be convergent. You can say it may be convergent, may not be convergent. This is the this is necessary condition. This is called necessary condition. So suppose this is one series, you are asked to test the convergence, that check whether this series is convergent or not. So what will be your first to check the limit n tends to infinity? What comes? Limit n tends to infinity even. That will be what? Tending to 1, which is not equal to 0. Not equal to 0 means know that if it is convergent, we must have this equal to 0. As it is coming, it is not equal to 0. As it is coming, it is not equal to 0. So that means you can immediately conclude that this series will not be convergent series. Okay, but suppose n is equal to 1 to infinity 1 by n. Here also limit n tends to infinity, the nth term un, that is tending to 0, that is tending to 0. So you cannot say, but when it comes out 0, you have to follow the next steps. You cannot conclude here that it will be a convergent series or divergent series. You cannot conclude. If it is coming not equal to 0, you can immediately conclude that it will be a convergent sequence. But if it is not coming 0, if it is coming 0, in that case you have to go for the further step. What is the further step? You have to test that series with the help of some test. We have three type of test. One is comparison test, another is D'Alembert ratio test, another is Cauchy's root test. We have to follow one by one others test, like you do in chemistry lab, that if this test fails, then we will do this test, like this. So for comparison test, we need to compare by two known series. First, we study these two known series. One is geometric series. One is geometric series. This is a one known series. So what is geometric series? You know the geometric progression, and that was up to finite number, that you know. Now, if the terms are in geometric progression, then that series are known as geometric series. Here you see this general format will be n is equal to 1 to infinity ax to the power n minus 1, a plus ax plus ax squared plus ax cube plus up to infinity. Those are geometric series where a is taking greater than 0. Okay, this series, there is a theorem that this series is convergent. This known series actually. Okay, you have to remember this convergence. You have to remember this convergence with the help of this geometric series, and another series is there. This is called P series. So using geometric series and P series, we will test some given other series. Okay, so what is the convergence criteria for this series? This series will be convergent if -1 less than x less than 1. So if it is convergent, then it converges to the value a by 1 minus x. So convergence criteria is only -1 less than x less than 1. If x lies, that means mod x less than 1. If x lies in between -1 to 1, then we say this series is convergent, and the value will be a by 1 minus x. And for x greater or equal to 1, that means for this value, this this is the line from -1 to 1, is x values. So for in this interval, we have x is convergent. For x from 1 to infinity, here we have divergent. Here convergent, here we have divergent. And for less than 1, it is not convergent, not divergent. It is not convergent, but more particularly, it will be oscillatory. It is really oscillatory sequence. For x is equal to -1, it will be oscillate finitely. For x is equal to strictly less than 1, it will oscillate infinitely. So for x less than or equal to -1, yes.
Can you explain the oscillatory point once?
I will explain. Completely explain. So suppose now, okay. So let me very try to much clear. Okay, you know the sum, this geometric progression sum. Suppose up to nth term, if you have up to nth term, that is, if I ask you what will be the sum a plus ax plus ax squared plus up to nth term, ax to the power n minus 1, n terms are there. What will be the sum that you know? Actually, I think you know this one.
Yes, sir.
The
Yes,
value
sir.
will be what?
Yes, sir.
That value will be
Yes,
x
sir.
to the
X to
power
the power
n.
n minus 1
Okay,
by
okay.
n minus 1.
By x minus 1.
By x minus
X
1.
minus
Okay,
1.
this is
n
the value.
minus 1.
Now, okay, now see, if this n tends to infinity, this n tends to infinity. If n tends to infinity, what will happen to this limit? If n tends to infinity, what will happen to this limit?
That depends on the
You
value of
see,
x. But a by x
exactly depends on the
It
value of
tends to
x.
infinity.
Depends on the,
if it is
no.
converging,
If
then
you see now, okay, let me see. if you see, if mod x less than 1, that means if the values are in between -1 to 1, not including -1 1 1, in between n to 1, in that case what happened, it will be like this form, some n to the power some 1 by y to the power n format, where y is some value. So in that case this xn tends to 0. Okay, yes or no? For mod x less than
Yes,
1,
sir.
we will have xn tends to 0.
Yes, sir.
Yes.
So in that case, in
Yes,
that
sir.
case, limit tends to a by 1 minus x. Okay, in that case only
Sir.
limit tends to a by 1 minus x.
Sir.
Now what happened if x is greater than 1? If x is greater than 1, what happened?
Limit tends to
If x is
infinity.
greater than 1, you see
Infinity.
direct goes to infinity.
Some will
So
be
direct goes to infinity means direct goes to infinity. So in that case, this limit tends to infinity, and we can say divergent.
Yes, sir.
Now you see what will happen for x is equal to 1. X is equal to 1, if you put denominator is 0, this one also 0. So I will not find from here. So what we will do from x equal to 1, if we put here x equal to 1 in this series, here if you put x equal to 1, if you put here, so it will be of the form a plus a plus a plus up to infinity. That means what? An limit n tends to infinity, that is tends to infinity. Yes or no? So for x greater equal to 1, the series is divergent. Understand up to this point? Now from for x is equal to -1, what will happen? If you put x equal to -1 here, it will be -2. Here we put -1, so -1 to the power n. So if n is even number, in that case the value will be 0. If n is odd number, the value will be minus a. Sorry, value will be a. Understand? So in that case, it will oscillate between a and 0. This summation oscillates between a and 0 when x is equal to -1. And if x less than -1, other some value, in that case it will tending to it will either minus infinity or plus infinity, the values. So it will oscillate between minus infinity and plus infinity. So you have to remember this thing. Proof is not required. You have to remember proof is like this. You can do like this. You have to remember it is convergent only when mod x less than 1, divergent for x greater equal to 1, oscillates finitely for x equal to -1, and infinitely for x is equal to x less than -1.
Sir,
Okay.
sir,
Next.
sir,
Tell me.
here I have a doubt.
Hmm.
Sir,
Tell me.
sir, yeah, a x n minus 1 by x minus 1. Tell me again here.
Which one? Which one?
Sir, it's a summation of a plus ax plus ax square plus dot 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 plus ax n minus 1 equal to a.
This is geometric series, no?
So second line.
You know, this one.
Yes, sir, this one.
This summation, you know this sum. You have studied in HS. In nth sum, you just check out. That is written. There's the nth sum for arithmetic progression, geometric progression. There you can find. Okay, here's the nth sum, the standard.
Sir. Hello, sir. I have
Yes.
a doubt. In second case,
Yes.
Can you explain again divergent y for x greater than n, greater than 1?
X greater than you just put x greater than 1. What will happen? X greater than 1 means what? Suppose you take one value, x greater than 1 means 2. So this is 2 to the power n. Yes. So if it is 2 to the power n, as n tends to infinity, 2 to the power n tends to what?
Infinity.
Infinity.
Yes.
So that's why it's tending to infinity.
Thank you, sir.
Sir,
Sir,
could
I
Now
you
come down to PC. Yeah. Hello?
Sir, actually, sir, you just said that if convergent a series, that it must converges to a unique limit. But when you are telling that necessary conditions, you are saying that limit n tending to infinity must be, I mean, un is should be equal to 0. Then it may be convergent, but
You
it's
have
not
you
equal.
have you have missed out things. Two things are there. One is summation un and another is simply un. Summation un tends to some finite value, then we say it is convergent. And the term un tends to must be 0. Understand? Summation even is the series itself, and even is the nth term of the series. Like suppose if I write 1 plus 1 by 2 plus 1 by 3 plus up to infinity. This is the un, summation un. And what is un here? The nth term is what? 1 by n?
0.
This tends to 0. Getting?
Mm.
Okay.
Sir, excuse me, sir.
Hmm.
Sir, please can you explain the case where x is equals to result formula a into x to the power n minus 1 upon x minus 1?
I'm not
That
getting.
case,
Which one you say?
result
Here.
formula.
Sir, we can.
The,
X is equal to for what happened for x is equal to minus 1? You're saying na?
no, x is equals to 1.
So he is talking about the
X is equal to 1.
formula of the
If you
divisor.
put x is equal to 1 here, if you put
Result
x is equal to 1
example
here,
a
what?
x raised to power n minus 1 of x
If
minus
in
1
x is equal to
example.
1,
Sorry.
then it is a constant sequence, then you can add simply.
Huh. So that's why I'm
Why are
telling
you
no. You
wasting
you
discussion?
just simply add. You just simply
Yeah,
add this nth sum. Suppose n terms
Okay,
are
sir.
there. N terms are so na. Now when n tends to infinity, it will tends to infinity. No?
Yeah, okay, sir.
That's why I'm saying. Okay,
Sir,
let me go
sir, I have a
to the
doubt.
next slide.
Sir,
Sir,
please, sir,
Sir,
Ah,
please explain the third one, second part.
third one, second part.
X less than minus 1. That one.
X less than minus 1 you do. What happen if x less than minus 1? Tell me. If
sir,
x less than minus
sir,
1, like that means you take minus 2 suppose.
Okay,
What will
sir.
happen? You put here minus 2, so it will be tending to minus 2. Now
Yes.
when n is even,
Hmm.
in that case it will tending to plus infinity. When n is odd, it tends to minus infinity.
Okay,
So
sir.
that's why
Hmm.
it oscillates in between minus infinity and infinity. So it's oscillate between minus infinity and infinity. That's why it oscillates infinitely.
Thank
Okay,
you,
let
sir.
me go to the next slide. Otherwise I'll not able to complete.
okay,
Okay,
sir.
now P series. Without proof, just you remember this thing. This is the P series. P series means 1 by format is 1 by n to the power p. Summation n is equal to 1 to infinity 1 by n to the power p. That means suppose
Sir,
p is equal
someone
to
making
1.
noise. Please
Then
stop them. Stop him.
okay, please unmute your microphone. All of you, please mute your microphone. Don't forget to mute your microphone. Just when you are talking to me, at that time you just unmute. Otherwise, always keep your mouth. Okay. Where am-
sir,
okay. So p for p is equal to 1.
sir.
Yes.
Due to my net connection problem, I cannot listen the class properly.
Okay. I will send you the video. Okay.
Okay, sir.
I'm recording this video. You will, and when you, I no need to send me the video. When you will having the your institute email ID, you will able to see all this video anytime. Okay, it will be all automatically uploaded in your account.
Okay, sir.
Anytime you can see. No issues. And that PDF I will send you always. Okay. For p is equal to 1, you can say what 1 by n, that is the series 1 plus 1 by 2 plus 1 by 3 plus like this. For n is equal to 2, 1 plus 1 by 2 square plus 1 by 3 square like this. So this is called a p series, and it is convergent when p is greater than 1 and divergent for p less than equal to 1. So for p greater than 1, that means for 2, 3, you can say for 1.5 also, 1.5, 1.6 if p value is 1.5, 1.6 is p value maybe 1 by 2 also. Okay, whatever, p is a real number. So for p greater than 1, the series is convergent. That is starting 1.1, 1.2. If p value is there, then this series is a convergent series. Otherwise, it will divergent. So now you see we have all the times talking about this one. This series is a divergent series because p less than equal to 1. So p is equal to 1 here. So this is a divergent series. So this is one counter example that when the nth term is tending to, however the nth term is tending to 0, but the series is not convergent. However the nth term is tends to 0. So nth term tends to 0 does not always imply that this will be convergent. It may converge, but if it is not tending to 0, it's surely divergent. Okay, now using these two series, using this p series, and geometric series, we'll have to study the test convergency test for other series. We have to study the convergency test for other series. We have three convergency tests. One is comparison test, then D'Alembert ratio test, then Cauchy's root test. Okay, so quickly, I have 2 minutes, so let me quickly explain this comparison test first. So comparison test, you see the name comparison test, that means you're comparing some with some known series. Okay, so what is the comparison series? One is two are same thing actually, but this is called direct comparison test. This limit form, two forms are there, same series, same test, but two forms. Direct comparison means, suppose two series are there. One is summation n series, n is equal to 1 to infinity, and another series we have summation bn, 1 to infinity bn series. And we know the term by term n always less than equal to bn for all n. Term by term we know n less than equal to bn. N less than equal to bn. If this happen, then this bn series will be convergent if you know that n is convergent. Sorry, if bn is convergent, if bn is convergent, then the bigger series is convergent. Bigger, you remember like this, if the bigger one is convergent, you see bigger one is convergent, so the lesser one follows him, the lesser one also convergent. If the bigger one is divergent, sorry, if smaller one is divergent, then the bigger one is convergent. N if diverges, then so does bn. So I am repeating once again, two series are there, n and bn. You know n less than equal to, if n less than equal to bn, then this bigger one bn, if it is convergent, if this b1 is convergent, then n also convergent. And for the divergency case, if smaller one is divergent, then the bigger one is also divergent. This is called direct comparison. Okay,
Sir,
and
what
this
about
is the
vice versa?
mhm.
What about the vice versa?
What about the?
If bigger one diverges, then what about the smaller one? In that.
No, that I am not saying. You see, actually, what happened? You will be having. You have to test one series. Suppose n. You have to test suppose 1 by n square plus 1 summation. You are asked to test whether this series is convergent or not. Okay, so you have to select. You have to choose some known series, and you have to check whether this an is less than or equal to bn or not. Like this. You see, n square plus 1, I can say n square plus 1 is always greater than n square. Yes or no? N square plus 1 always greater than n square. So immediately you can say 1 by n square plus 1 is less than 1 by n square. You see, this is your given series. So here we have, if I choose an is equal to 1 by n square plus 1 and bn is equal to 1 by n square. So an less than equal to bn, and you see this bn series is your known series. What is that? P series, and p value is 2 here, this is P series, yes or no? This is a P series and P value is 2 here, which is greater than 1. So you know that Bn is convergent. So if you know Bn is convergent, so the bigger one is convergent.
So I have a doubt about the P series, that if the P value is greater than 1, how is it convergent?
Oh, that I've told you that that is actually without proof I am doing this. This is actually a theorem, you can say. This is a result. And the proof I am not included here because the heavier proof, this is a 3-4 page I need. So one class required to explain the what the proof of this theorem that I can do later on. If you want, I can do in some other time. Okay,
Okay, sir.
some evening time I can do it.
Okay, sir. Okay, sir.
Okay, but and you can
Okay,
find
sir.
from any book. This you can consider as a theorem. Okay, for the time being. Okay,
Sir, when
so
is in one,
uh,
why not is
what
sir, when
your
the
sound
P
is not
value
clear.
is one, why not is sir,
When the p
when
value
the
is
P value is one,
uh,
then why not
uh,
is convergent?
that I have told you, na. Repeatedly, I'm telling you that all are depends on the proof. If you go through the proof, then you can see. Okay, I will do one thing. I will give you the proof also while sending you this PDF. I'll send you the proof also. Therefrom, you can you just check out whether you have, if you understand. Okay, well, if you do not understand, you can tell me. But that I will do only in some other evening class or sometime, not in the regular class. Okay, because one class I will require for that purpose, for particular that's proof. So that's why I'm telling you that you keep this as a result. Okay. Okay. Now, okay. So here you see. So you need to compare like this. So you have to compare this series with some known series. Here I am considering with 1 by n square. So Bn is convergent. So I can say An is also convergent. But if you want to show some series divergent, in that case you need to bring An greater equal to some Bn, and Bn will be known. Okay, so this is the comparison case. The direct, and for the indirect, you see, not indirect, limit case, what you have to do. Okay, one more important part, this test, whatever comparison test, D'Alembert ratio test, and the Cauchy's root test, all are for only the series with positive terms. Series with positive terms. You see, we have taken 0 as not the alternating series. Okay, if 1 minus 1 is the minus is there, it's not hold. So it is all about the positive series, this test. So now, what is the limit test? That if limit n tends to infinity, an by bn is equal to some finite value L. If limit n tends to infinity, an by bn is equal to some finite value L. This finite value L, not where L is not equal to, remember, L is not equal to 0 and infinity. L is not equal to 0 and infinity, some other value. So in that case, either both are convergent or both are divergent. Can I make it clear? Suppose here an is equal to, we have 1 by n square plus 1. If you choose bn is equal to 1 by n square, you see limit n tends to infinity, an by bn, this is equal to what? 1, which is not equal to 0 and infinity. So you can say both the series are convergent or both the divergent, or both are convergent or both are divergent. You see, but you know that bn is convergent, so you must have an is also convergent. You know bn is convergent, so you must have an is also convergent. Now there is a note, and right, this is very important. Try to bring, when you are using limit comparison test, try to bring this L. Try to bring, I will explain with an example later in next class, but for the I will stop after this. So when L is there, try to bring always this L is equal to some value other than 0 and infinity. But if somewhere you have L is equal to 0, if you have L is equal to 0 coming, in that case also test valid only for the convergency case. And when L is equal to infinity, in that case also test is valid, but only for the divergency case. Understand? That means if L is coming 0, in that case you can say both are convergent. If Bn is convergent, then you can say An is convergent. If An is convergent, then Bn is convergent. But if Bn is divergent or An is divergent, you cannot say another one is divergent. For L is equal to, when L comes 0. But when L is equal to infinity, similarly for L is equal to infinity, when L comes infinity, in that case you can say both are divergent, but you cannot say both are convergent. So this you have to keep very cautious about when L comes either 0 and infinity. Either other than 0 and infinity, you can directly some finite value other than 0 if you have, you can say directly that both are convergent or both are divergent, and one will be known to you, so another one immediately follows. Okay, so
Sir,
I'm not
if L
going.
comes negative,
No, L comes. L comes. No, L will not come negative because I am considering both are greater than 0. Na? A and B and both are greater than 0.
So,
L cannot.
Sir, can you explain the note again?
This note against, you see,
Yes,
I am
sir.
writing here both. Here I am writing both. Both are convergent, both are divergent. No? That means if L is other than 0 and infinity, finite value other than 0, in that case both are convergent, both are divergent. You don't have to bother about it. But if comes either 0 or infinity, if comes suppose 0, in that case this both will not going to happen. In that case it will be for the test valid for the convergency only, and when L is infinity, it is valid only for the divergence only. That means if L comes 0 and you know that Bn is a divergent series, you cannot test with this comparison test. Test fail. In that case, test fail. Simply say. And if L is infinity and you know that Bn is convergent, in that case also this test fail. But test valid if for L is equal to infinity, when only for divergence case, for L is equal to 0, only for the convergence case. Okay.
Okay, sir.
Okay, sir.
So let me with this let me stop here. You have next class now, so I'll stop here today, and I will send you this PDF later on.
So from where we
So
should
let me
start
stop today.
practicing?
Hmm?
So from where we should start practicing these sums one by one?
You can take any book. Some books are given. Last I have discussed that Crazy book you can take, or whatever any book. I will supply some material also,
Okay, sir.
some problems also. But you can keep any book, no problem.
Okay, sir. Thank you, sir.
Sir, name reference material, no sir.
Huh?
Sir, may I use Rambabu book? Rambabu.
Babu.
No problem. Any book
That's
you take.
Baburan.
But you see,
Oh, sorry.
Baburam. No problem. When you will come to your NIT Durgapur, when you will come, when physically you come NIT Durgapur, there you will get lots of local books there also. You
Sir, I
can
have a
take
question.
that also. Hmm?
Sir, I have
Sir,
a
from
question.
Central
It's from Central Library.
Sir,
And for the primary, yes, tell me.
the geometric series में जो question है,
What geometric series?
geometric series में convergency में mod x less than 1 by
हाँ
so a by 1 minus x convergent ये कैसे हो रहा है?
हाँ
तो ये कैसे?
mod x less than 1 होने से mod x less than, if it is mod x less than 1,
हाँ
if it is mod x less than 1 and you have x to the power n, as n tends to infinity, what will happen to x tending to 0 or somewhere else?
अच्छा अच्छा
Tell me. Suppose mod x less than 1, take any particular value 1 by 2. So 1 by 2, that will always tend to 0, na?
हाँ 0 0 वो हाँ ठीक ठीक तो n equal to
Okay.
even होना चाहिए
L
मैं माने
even odd कुछ भी हो, even odd कुछ भी हो,
अच्छा ठीक है sir.
इवन आउट तो सिर्फ नेगेटिव के लिए कम करता है ना, इवन आउट तो ओनली फॉर द नेगेटिव वैल्यूज और
यहाँ पे mod x है
एप्लीकेशन
mod x हाँ, ठीक
हाँ mod x है तो ठीक
हाँ
है, कोई बात नहीं, -1/2 ले लो, 1/2 to the power n भी सेम है।
अच्छा अच्छा थैंक यू सर हाँ
That's why.
Sir,
Okay, let's talk
Excuse
about
me, sir.
बोलो।
I have a doubt, sir.
बोलो।
Actually, sir, same doubt, sir. The last term of a series, if it tends to some finite value, why don't it become a convergent?
Which one? Where you are saying?
Just said that limit n tending to infinity un equals to 0, the series may be convergent, and if it is not equal to 0, it won't.
You are very much confused about these two things. Actually, I am saying you see.
Sir, I am also
We have the
confused if you can
series.
better.
You see, what? Hello, someone is saying
Sir,
the
I
sound
said
is
I
not
am
clear.
I
The
said I am
sound is
also
not clear.
better. So I'll say that later.
Hello. Okay, let me explain this thing once again. Limit n is equal to 1 to infinity un. Okay, this thing, one thing, and limit. If I say limit n tends to infinity un, that means what? If the nth term of this series, yes or no? You see, 1 plus 1/2 plus 1/3 plus up to infinity. What will happen to this sum? What will happen to this sum? That is equal to, suppose, some s. If s is tends to infinity, if s is tending to infinity, then means it is convergent. If s is tends to some finite value, s is some finite value, then it is convergent. Otherwise, it is divergent. But un is what? The nth term. What is the nth term of this series? That is 1/n. This may tends to 0, no problem. This have to be tends to 0 for convergency. This have to have tends to 0. This is the necessary condition, but
Sir,
not
I am
always
saying that
holds.
if the last term is tending to, let's say, 1 or 2, then why it doesn't become convergent? I mean, it.
Okay. That part is actually included in for the proof. You are just seeing. Okay, I understand that. You are saying that this is half. This is 1/3. The values are decreasing.
Hmm.
The values are decreasing. The values are decreasing. So why it is not? It may be. You can say that it may be some value 1 plus some 3. It may
Yes,
goes
sir.
to
Yes,
that
sir.
value. That is your concern, na?
Yes, sir.
You see, that may happens like this, that the value is coming fast. If you take up to 100 terms, the values is coming, suppose you can see the values is coming, suppose 1.1234 like this. I'm saying then
Okay.
for 110 terms, 110 sub you take, it will be maybe 1.1235. 120 times 1.1, the increasing may be the increased value may be very small, but it is always increase as you go. It is not going to the fixed value. It will not going to the fixed value. That is the point. Understand?
No, sir.
The increment may be very small. Increment it will always have some increment. Okay, as you take some n tends to infinity, na,
Yes,
it
sir.
always have some increment. But for the convergency case, after some finite value, it will not having some any increment. It will going to the fixed value.
Okay. No, so let's just say the series is given like this. The first term is 2, then it is from decreasing and when n tends to infinity, it becomes 1, and then we have to find the summation. Then in the case that the series will be convergent or not convergent.
I'm not getting what.
Say, let's say this, the first term of that series is 2 or 3,
True.
and it is constantly decreasing. I mean, decreasing in a certain manner that
1 by
the
2.
last term or the last term is tending to 1. Actually,
Last term is tending to 1, then it will not converge.
but sir, the summation will be. I mean, it will be something. Oh, it might become infinity in the case.
Yes.
Yes. Yes. Yeah. Now I understood. Sir. Yes.
Understand? Okay.
Yes, sir.
Sir,
Okay,
how
let's
will
stop
it
here
be?
today. You can leave the meeting.
Sir, he said that it will become infinity till the end. How it will be infinity then?
Not
So,
not infinity. I am saying like this. One suppose the last value is tending to 1. But 1 by 2, 1 by 3 is there, 1 by 4 is there, so always it is increasing, always the values are increasing, the values are increasing, there is always have some increment, that is the point.
Excuse me, sir.
And
okay.
always have increment means what? And always have increment means what? If you have always some increment, that means it is going to infinity.
Okay. Sir,
Undefined thing.
sir.
Yes.
In this case, I mean here 1 plus 1, 1 by 2 plus 1 by 3, sir. Here, since the sum is increasing, so it is not convergent. So, sir, in that case, that 1 plus 1 by 2 square plus 1 by 3 square, in that case also increment will be there, sir. Sir, it is
That is the point, that is my point, that if you go through the proof, you can see there, if you go through the proof, you can see there, for p when this p is greater than 1, when is p is greater than 1, there is no increment in like this, and you are getting a fixed value, going towards a fixed value.
okay, sir.
Okay, for p less than equal to 1, you will have some increment. That is my point.
Okay, sir.
Okay, okay, you just go through once the who are not have some confusion, you just go through once, not no need to for the exam preparation, just go through the proof once, you will be able to understand, I think. If you not, you tell me, I will discuss this theorem in some other time, free time.
Sir, please send us the slides.
Okay, sir.
I will send you, but maybe by evening. Okay, I will
Okay,
having class
okay, sir.
some now, maybe this slides by evening.
Okay.
Okay, sir.
Okay, sir. Thank you, sir.
Let's stop here today. Okay.
Okay, sir.
Thank you, sir.
Thank you,
Thank you,
sir.
sir.
Thank you,
Okay.
sir.
Thank you,
Thank
sir.
you, sir.
Thank you,
Thank you,
sir.
sir.
Thank you, sir.
Sir.